We're doing this deep dive today into something called triage from ABBA data. What's interesting is how they bring in reliability engineering to classify the hazards for these non-metallic lines.
We're going to dig into what functional failure actually means,
Mhm.
how they use this reliability-centered integrity classification thing, the differences in performance between pipe types like spooled fiberglass versus these fiber composites,
It's a big difference there.
and those specific issues in oil emulsion gathering or high-pressure water injection, things like terrain-induced slugging and water hammer.
Can be really rough on the system.
Okay, so let's start there. How does triage actually use reliability engineering principles to get beyond that simple pass-fail?
The core idea is moving away from just a snapshot. Triage uses these reliability concepts so you can view integrity as moving along a scale. Think like healthy, then maybe becoming functionally compromised so it's not broken, but it's not performing like it should.
Not optimal.
And then eventually it could reach actual failure. The whole point is to catch things before you get to that final catastrophic stage.
Makes sense, catching it earlier. So what are the specific reliability ideas they're actually plugging into triage?
So there are a few key ones. One really important concept is something called PC interval mapping. Now, people might know PF, potential failure, from other areas.
Yeah, I've heard of it.
So triage adapts this slightly to PC. P is the point where a potential problem becomes detectable through an inspection.
Okay.
And C is when you get a catastrophic failure, a rupture, a major leak. So by mapping this P to C time frame, they can classify pipeline sections that are already showing signs of degradation before they actually rupture.
I see. So it's not just, is there a flaw, but how far along the path towards big failure is this flaw?
Precisely. That's the idea. Then they also use Weibull distribution curves.
The modeling failure rates.
Yeah, basically. Think of them as models built from historical data. They help predict how likely a specific material is to degrade or fail over a certain time period. So for a given type of non-metallic pipe, they can model its expected degradation path.
So you move from just hoping it lasts to having a data-driven idea of its lifespan.
Exactly. It helps make maintenance scheduling much smarter, and conceptually, they also use Markov chain transitions.
Oh, okay, that sounds complex. How does that fit in?
It's about modeling probabilities. Think of the pipeline's condition as different states: healthy, slightly degraded, compromised, failed. The Markov chain helps model the probability of a pipe segment shifting from one state to another based on various influences.
Okay, the odds of it getting worse over the next year, maybe?
Yeah, it represents those dynamic shifts. And finally, it all ties into a risk-based inspection philosophy.
Focusing inspections where the risk is highest.
Exactly. So how often you inspect and what methods you use isn't just on a fixed calendar. It's guided by the predicted degradation rate and the specific vulnerabilities of that pipeline section. Functional failure in the triage model means the pipeline isn't meeting its intended operational requirements, even if it hasn't physically ruptured. Maybe the pipe is still carrying fluid, but some deformation. Or perhaps it's experiencing excessive bending or strain in one section, which hasn't caused a leak yet, but indicates it's no longer structurally sound for its purpose. And that PC curve methodology we talked about, it's specifically geared towards identifying those segments that are in this functionally failed state well before they hit the C, the catastrophic one.
It really shows the value, doesn't it?
Absolutely. It's about maintaining efficiency and preventing escalation.
Now, the sources mention differences between pipe materials, specifically spooled fiberglass versus these fiber-spooled composites. What are the key performance differences triage looks at?
This is super important because the materials behave quite differently. Spooled fiberglass. It can be a cost-effective choice sometimes, but it has known vulnerabilities.
Like,
The manufacturing and installation process itself can introduce micro fissures, tiny cracks, especially during unspooling and bending it into place.
okay.
It also generally has lower mechanical resilience, meaning it doesn't handle things like temperature swings, thermal cycling, or bending stresses during operation quite as well. And critically, it tends to have a higher tendency to fail quite suddenly under sharp pressure increases, like water hammer or slug events. This is a big deal in water injection or oil emulsion lines.
So maybe a bit more brittle, less forgiving?
Generally speaking, yes, less ductile. Now, compare that to the fiber-spooled composites. They're engineered differently. The fibers are wound like a spring pattern.
Okay, and what does that do?
That helical winding gives them much better ductility. They can stretch or deform more before failing, and much better energy absorption, so they can handle sudden impacts or pressure surges better.
Okay.
And that construction also makes them more resistant to progressive delamination, where the layers of the composite might start separating. So the bottom line is these fiberboom composites usually have significantly longer PC intervals compared to fiberglass under similar conditions. They tend to degrade more predictably and are less prone to those sudden, brittle failures from pressure spikes.
That material difference must have a huge impact on inspection frequency and overall confidence.
Absolutely, it fundamentally changes the risk profile.
But it's not just the pipe material itself, is it? The sources also talked about how the pipeline is installed and its configuration. How does triage factor that in?
Oh, definitely. The context matters hugely. How and where the pipe is put in the ground is critical.
So like the trench conditions.
Yeah, exactly. For instance, if you've got a composite liner pulled inside an old steel pipe, a common rehab technique, triage looks at the risk of that liner shifting axially, or if pressure builds up in the space between the liner and the old pipe.
Okay.
Then there's the actual path, the right-of-way. Is it going up steep slopes? Even things like the quality of the backfill around the pipe. Poor backfill can lead to point loads or uneven support, causing bending.
Lots of potential stress points.
For sure. And then there are the termination risers, where the buried pipe comes up to connect to equipment above ground. Triage assesses these very carefully. How well are they supported mechanically? Are there points where stress concentrates? How is thermal expansion handled? They even look at the track record of the specific types of connectors used.
Wow, okay. It really sounds like they're trying to capture the whole picture, from the material science right through to the specific spot in the ground.
That's the goal, a holistic view of integrity.
So let's talk about those specific service conditions: oil emulsion gathering and high-pressure water injection. What are the particular hazards triage zooms in on there?
So oil emulsion gathering systems, they're a tough environment. You often get significant temperature swings as production cycles up and down.
Thermal stress.
And you get these things called hydrocarbon-laden slugs, basically pockets of gas, oil, and water moving together, which can cause pressure and flow to fluctuate quite a bit.
What about the high-pressure water injection lines? Different set of problems.
Different, but just as challenging. The big one there is the frequency of pressure spikes. These systems operate at very high pressures.
Yeah.
And pump starts, stops, valve operations, they can all create really rapid pressure surges.
Water hammer. That's it.
Water hammer is definitely a major concern, especially the shock loading it creates at bends and fittings like termination risers. And if the pipeline isn't properly restrained, these pressure waves can actually propagate along the pipe, causing fatigue damage over time, especially at joints or connectors.
I see.
And triage specifically tries to differentiate the impact of severe terrain-induced slugging, which is about large volumes of liquid moving due to elevation changes, versus those very fast, high-frequency pressure waves from water hammer. They affect the pipe differently.
That level of detail is pretty impressive. You can see how just a basic pass-fail inspection would miss all that nuance.
Completely.
Let's go back to that PC curve again. You said it visualizes that time from detection to potential catastrophe. How does triage actually use that curve to assess risk and guide actions?
Yeah, the PC curve is the backbone for how triage assesses that functional failure state. It's used to calculate a severity index score for every segment of the pipeline.
The score. Okay.
And this score isn't static. It can change dynamically based on new inspection data and the known susceptibility of that material in that environment. This lets triage flag segments that are likely already in that functionally failed zone, even if no leak has occurred.
Got it. So it flags the ones getting close to or past their functional limit.
Exactly. And then the system overlays inspection interval recommendations right onto that curve. These recommendations are based on the modeled degradation rate, how fast they expect that specific pipe section to degrade under its current operating condition.
So if you have, say, a fiberglass pipe in a high-stress water injection line, it would likely show a shorter PC interval and trigger recommendations for more frequent inspections.
Precisely. That's exactly how it works. The beauty of the PC curve is it gives you that clear visual. You can immediately compare materials, see which ones tend to have shorter versus longer effective lifespans in similar services.
Yeah.
It helps operators grasp the urgency
Yeah.
to compare material performance and communicate the risk and the degradation status clearly to everyone involved.
And I think you mentioned earlier that triage separates the risk along the pipeline route itself from the risk at the endpoints, the risers.
Yes, it does. It makes a distinction between the right-of-way, integrity risk, which is more about those external factors like terrain, installation quality, service
A
loads,
buried part.
and the termination riser risk, which is more focused on the riser's mechanical design, how well it's restrained, the connector type and condition, and how it handles pressure fluctuations. Each segment gets its own individual score for the likelihood of functional failure. This is all visualized in the triage interface. Operators can immediately see, like on a map or a dashboard, which areas are scoring higher and need priority attention.
So it really helps them focus their efforts. What kind of actionable insights does triage give the operators on the ground?
Well, it leads to very concrete actions. For example, the system might highlight specific segments of composite pipe that the models suggest are probably already in that functional failure zone. It allows for targeted inspections or maybe deploying different, more advanced inspection techniques just on those high-risk segments instead of having to do the whole line.
More efficient.
Much more. Or for termination risers flagged as high strain, or maybe use a connector type with a known history of issues, triage might recommend proactive replacement even before a problem occurs.
Right.
Ultimately, it lets operators tailor their entire integrity management program, the inspection frequencies, the methods, the repairs, based on this much deeper data-driven understanding of material behavior and predicted degradation in their specific context.
Thanks for joining us on The Deep Dive.